Chapter 9 is what we're going to do today, what we're going to try to start at least. We won't get finished, but we will start. And sort of everything that we've been doing, especially since the midterm, has been building up to this. So it will require that, you understand a little bit of 6 and 7, especially if you understood 8. I would say a lot of that will carry over into what we're going to do with inferences and hypothesis testing. So hypothesis testing, we've sort of started a little bit about our hypotheses already. Last time when we collected data and we used it for the confidence interval activity, before we started collecting data, we decided what our hypotheses were. And those hypotheses are what we're going to use this time. So any educated guess is sort of a hypothesis. And we did that for the activity and we did that for projects as well. And then today will explain a lot more detail about what hypotheses are, how we can test them, and that sort of thing. So our first 2 sections are looking at the steps of doing a significance test and how you go through that. The second thing that we'll talk about is focusing in on proportions and doing examples of hypothesis tests. So the first section is really just sort of a laying out of the process. We'll actually start using the process in section 2, and then in section 3, we will do significance tests for mean data. So we have proportions and we have means, like we have different methods for confidence intervals, we'll have different methods for hypothesis tests. And this is really just a huge carryover from Chapter 8. We won't do, we're going to leave out these 3 sections so we can really focus on the core stuff, the first 3 sections. So the last 3 sections of Chapter 9 we're leaving off, and of course we're leaving off Chapter 10, which is a different sort of hypothesis testing. We will only really do the 2 different sorts, the proportions and the means. Oh, sorry. I need to update my slides, don't I? But some people use my slides. Well, some people might use my slides. I haven't opened them.
Oh, you know what you have? Those and
3. Yeah, it's a lot of material for 9-1. Yeah. What are the steps for performing? So this first section, just talking about the steps. So, of course, we're going to talk about the 5 steps of the significance test, and the 5 steps are these. Number 1, we'll talk about assumptions, then hypotheses, then how to calculate the test statistics and the p-value, and then conclusions that we're going to draw about the significance, the statistical significance. So, significance test is sort of like what I told you. You formulate some hypothesis about your data. Hopefully you do that before you even look at your data, and then you go through the steps of the significance test to see if you can prove your hypothesis. And we won't prove beyond any amount, but we will prove with a reasonable amount of confidence that our hypothesis is true. And then the steps to doing that are you've got to make sure that your assumptions are met, and we have very similar assumptions that we had for Chapter 8. You've got to formulate your hypotheses before seeing the data, and then this is what you do with the data. You use your sample data to compute a test statistic, and we'll talk about what that is. You also use your sample data and compute a p-value, and then based on that p-value, you will draw some conclusion. Are you able to say that you've proven your hypothesis is true, or do you have inconclusive data? So the first step is our assumptions, and we really shouldn't do the hypothesis test if our assumptions are not met. So for any hypothesis test, no matter what you do, you've got to have random data. If your data are not collected randomly, then your data do not represent the entire population, and we can't do analysis and make good predictions without that. So any hypothesis test needs random data. And then, the second assumption is that you might need a large sample size, like we do for when we're doing means. As long as we have 30 or more, we're generally good. And sometimes we can have even less than 30 if we have a sort of normal distribution to start with. And then the shape of the distribution matters. So with the shape of the distribution, if you've already started with a normal distribution, you may not need a larger sample size. With proportions, we'll find out that we need at least 15 successes and 15 failures, like what we did in the previous chapter. So those are sort of the general assumptions that any hypothesis test will have. And then the actual hypotheses, you're going to make some statement about a parameter. And what's a parameter again? There are two examples of parameters listed up there. Yeah, it tells some measure of the population. So you're going to make some guess, educated guess, some hypothesis about the population measure. You might say that the population mean is more than 37, or the population standard deviation is less than 2, or the population proportion is more than 1/2, or something along those lines. And some statement about a population parameter. And there are actually two hypotheses. I only had to make one hypothesis when you went around and collected your data, and I only had to make one hypothesis before you started for each of your data sets, before you started to do your project this time. But that's the important one that I had you make. The important one, the one that we're trying to prove, is this alternative hypothesis, 8A. And the alternative hypothesis is really the only hypothesis you can prove. We have the null hypothesis, which is sort of the antithesis or the opposite of the alternative hypothesis. It's what we assume might be true if we're not able to prove the null, but if we're not able to prove the alternative, but we never really say the null is true. We never really know if the null is true. And the reason for that is the null always says that the mean is exactly equal to something, or that the population proportion is exactly equal to something. And it's difficult, really impossible, to prove without 100% of your data that anything is exactly equal. Because if you did a sample, the population only had, say, 35 people, and you were able to survey 34 of those 35 at random, and you had a mean exactly equal to 0, you still don't know, and it's doubtful even that your whole population would be exactly equal to 0 because you didn't do that last person. So even just one person can make exactly equal be wrong. But you can make conclusions like the mean age of this class, we would say, would be less than 100. We could probably not even gather data and say, oh yeah, well that's obviously going to be true. Or the proportion of people who are going to make an A in this class is going to be greater than 0. We could collect some data and see that that has a very good chance of being true. So those sorts of things, when we do greater than, less than, or even not equal to, these three things are what alternative hypotheses are, and we can prove alternative hypotheses. So that's really our thrust. We make those hypotheses, but our goal is to prove the alternative hypothesis. We make these before actually seeing our data, ideally. I know we didn't do that in the project, but if you were doing a real research project, you wouldn't even want to look at the data before you make these hypotheses. Because if you do it sort of hindsight is better than foresight, you haven't really proven much of anything. You've just shown that you've analyzed your data. So it's better to make predictions and then have your predictions be supported by the data later on.
So would you do this before you actually did the survey, or would
Yes.
or would you want the data like before you even do it?
Ideally, I should have had you make the hypotheses, and I may move that, but I feel like that's sort of a lot to throw on you when you don't have a really good feel for data in general, to have you make hypotheses. But maybe I will change that at some point and have that be part of the pre-project report of what do you think this data is going to look like. Yeah. We'll come. This will be at the end. It'll all make sense at the end. But yeah.
Or maybe if we know our data, so maybe if you have a switch with another group data,
Oh yeah.
that could be a possibility.
Yeah, you could have.
Yeah.
Yeah. Some people have already done their mini tab and stuff, so we're not switching this year.
No, I mean.
But I'm looking for ideas for next year. Yeah.
Like next semester or something.
Yeah. Absolutely.
Oh, my bad. We're not gonna be there.
So it's best to formulate before seeing, and again, our goal is to prove the alternative because you can't really prove the null. The third step is the test statistics. And we've talked about statistics before. Statistics go with samples like populations go with parameters. So a statistic is some measure of our sample. Here, the statistic is the measure of how far our data is from our mean or our hypothesized mean. So we will actually assume that the null is true here. So let's suppose our null was that p is greater than 0, or that's our alternative, sorry. And then our null would be p equals 0. And so this would be 0, the hypothesized mean. Then we would compute a test statistic using our real data. So let's say our real data was some positive number, not 0, but some positive number. We compute our test statistic, and our test statistic we're familiar with from the last chapter. It's going to be either Z or T. So Z or T tells us how many standard errors we are from our mean, proportion, population proportion, or what we think is our population proportion. So we're actually assuming something that we think is false. We think the null is false. We're assuming that it's true, and we're hoping to find some sort of contradiction here. Some sort of, our data say that it's implausible, it's unbelievable, this is true. So we compute the T, tell us how far it is. If it's really far away, like, especially if it's more than 3 standard deviations away, 3 standard errors away, then we would say it's not very believable, right? Yeah, if our data is that far away, far enough away to be considered an outlier, then the probability of the null being true is very low. And in that case, we say that we've proven our alternative. We say, oh, the null is not believable, so we reject the null hypothesis and we accept the alternative. Particularly, we calculate the area to the left of our test statistic. So here you have your test statistic, or to the right in this instance. We calculate the area in the direction of our hypothesis. So since it says greater than here, we're going to calculate the area that's greater than our test statistic. And that area greater than would be the p-value. So that brings us to our next p-value. We just calculate this area. And if we were doing that, we could use which calculator function?
Inverse norm.
Is it inverse norm?
Normal CDF.
Normal CDF, because we would already have our T or Z score. And we would use normal CDF, or in the case of T, there's a T CDF, but we will actually use a different method by the time we get to that chapter. But for Z, definitely normal CDF. And we put in this is our minimum and infinity is our maximum, and that will give us the area, 0, 1, because this is the Z-curve. And that area, if it's large, the area literally represents how likely we are to have data that's as extreme as it is, if our null is actually true. So it assumes the null is true. What's the probability that our data would look like this? And if it's a very small probability, we're probably going to reject the null. Because the smaller the probability that our data is that extreme, is a relationship with the smaller the probability that the null is true. So large values like 40, 50%, even 30%, maybe even 20%, we would say, well, that's a really good chance, 20% that it would be that extreme, so that's not, in fact, that extreme. When you get to 10 or 5%, a probability of 0.10 or 0.05, that is such a low probability of happening that we say, ooh, maybe we should reject the null. So different people will have different standards, and we'll talk about that in the next section about what's your standard, when do you really cut off. But almost everyone says, 0.3, 0.4, 0.5, anything more than that, that's just too much. There's no way we're going to reject the null. It's just not enough evidence there. But 0.05 or less, people usually say, yeah, there's really good evidence against the null here. We'll think about rejecting. So that's the p-value. And then your conclusion will be looking at the p-value, looking at what your threshold value is and comparing the two and deciding, how strong is that p-value against the null? And then writing up, yes, we can conclude that the alternative is true. Or if the p-value is larger, you'll have to say, no, there's not enough data to conclude that the alternative is true. So we usually phrase things in terms of the alternative. That's our important hypothesis. So think always in terms of the alternative. The null is just there as sort of the opposite of the alternative. So our conclusion, were we able to prove or not alternative hypothesis? And so here are a few examples before we get into actually working through a hypothesis test of the sort of things that we talked about. And here are 3 hypothesis statements, and we want to know if they're null or alternative hypotheses and why. So the first one, the mean IQ of all Lake Wobegon students is larger than 100. What would that be? Alternative. So we write that as HA. And then the probability of rolling a 6 with a particular die equals 1/6. The null. And why is that? Yeah, it's exactly equal. And this one, because it says larger than. And then the last one, the proportion of all new business enterprises that remain in business for at least 5 years is less than 1/10. Alternative. That's kind of sad if that's true, isn't it? Very, very risky. People look if that's true. Any questions on these?
So greater than would be an alternative.
Greater than, not equal to, or less than.
Null.
Mm-hmm. And then the only one that would be a null is exactly equal to. HO, yeah. O meaning 0, null and void, so null, 0. And then A, of course, meaning alternative. Okay, here we have study plans to sample obese people and who are on a diet, and they'll measure the weight at the beginning and then the weight at the end. And then what's actually being recorded is the mean change in weight. And they're doing that, calculating the weight change, by doing start of the study minus the weight at the end of the study. But what they're saying is that that mean weight change is a positive number. So would this be considered a null or alternative hypothesis? Alternative, why?
It's above a certain.
Yeah, is positive literally means greater than 0, right? Define a relevant parameter. So what parameters have we talked about in this class?
In the,
I'm sorry?
mean and,
Mu, specifically the mean mu that represents the population mean. And that's the one that we want here, right? Because it says the population mean right here. So mu is our relevant parameter that we want. And express the hypothesis that the diet has no effect. So how would we write that hypothesis?
If you didn't go,
It would be, but what else, what would the statement actually say?
that, right, I mean, 0 is greater than
Equal to 0, but what is equal to 0? Yeah, the mu.
I was wanting to say you, but I was wrong.
Yeah, mu, so really a hypothesis statement has a left side, a symbol, and a right side. The left side is always going to be a parameter, either mu or p in our cases, because those are the only two types of hypothesis we're going to do. The null always has the equal sign, and then what it's equal to, your hypothesized value. Heather, did that answer your question?
E is population.
P is population proportion. Proportion more specifically. This is population as well, but it's the mean. Other questions? A lot of people struggle with knowing when to put what where. So when they're doing a proportion example, they might put mu, and when they're doing a mean example, they might put mu. So watch that. Mu is for when you're taking averages, when you have numerical quantitative data. P is for when you have categorical data and you're taking proportions. And then, is this, oh, you've already said it's the null though, right? Okay. Here is a question about test statistics. Let's suppose that our null hypothesis is that the proportion of the population equals 0.50. The test statistic is a z-score, like we talked about, that measures how many standard errors you are from the mean, or in this case, the proportion, population proportion, with your actual data. And here, our z-score is 3.6. So what would we say? Do the data support the null hypothesis, or do they provide strong evidence against the null? Yeah, strong evidence against it. Why?
But 8 is greater than, or 8 is greater than 4.
Well, even if it weren't, it could be, you know, I guess it theoretically could be less than, but surely it's more than or not equal to one of those two. But it's mostly because if you're right here with your HO, you have to go out positive 3.6 standard deviation. So that's well after the curve has sort of leveled off. Because your sample data is so far away from the hypothesized mean, it's very unlikely that your hypothesized mean is correct. Okay, does everybody understand why that is now? So 3 standard errors is really far. That's why we've defined outliers to be more than 3 standard errors out. Really, we often reject way before it gets to 3.6 standard errors. And then here are p-values. P-values are different from what we just talked about, the z and the t. The p-values are the area. So if it had said greater than, so that's 3.6, if it had said greater than, we would have shaded this area for the p-value. So what would we say about a p-value of 0.38? Would it provide strong evidence or not especially strong?
Smaller the number, the less likely, so greater the number.
You said like 0.5 or higher would prove it wrong, but if it's like 0.38.
0.05 or higher. 0.05, I believe. Yeah, yeah. So this is actually not especially strong, not that strong. Yeah, 0.001 is actually very strong. And the reason for that is that 0.38 means, what this literally means is that we're assuming the null is true, there's a 38% chance that my data would be as extreme as it is. Well, 38% chance is a really good chance, a really strong chance. So that sort of supports the null. Now, we never proved that the null is true, but we certainly aren't disproving it by saying it's only a 38% chance that we get. That's not that extreme. What the second one's saying, though, is that there is less than there is a 0.1% chance that we would have data in this extreme. 1 chance in 1,000 that we would have data in this extreme if our null were true. So that the 0.1 actually contradicts the null and supports the alternative. Are there any questions? Any questions? So now we will talk a little bit about proportions, significance tests about proportions. And so for this section, we're going to actually go through an example for all of these steps. Our objectives here are to cover the steps of the significance test for proportions specifically, and then walk through an example of how you would do proportions. And then number 2, we want to interpret what the p-value means. So we've talked about it sort of in arbitrary terms. We want to sort of concrete that up and cement it and give you some really good information on what p-values are acceptable and what are not, for when you'll reject and when you won't. And then we'll talk about the two-sided hypothesis test. We haven't talked about that yet. We'll talk about p-values for different alternative hypotheses. So when it's less than, greater than, not equal to, what do you do differently for those? We'll talk about the significance level. And the significance level is another little Greek symbol, alpha. Not very good, alpha. It looks sort of like a cursive A. It actually is A in the Greek alphabet. The first letter of the Greek alphabet, and it's lowercase alpha. And that is what we'll compare to P to decide, hey, is P small enough to reject the null enough? And then we'll talk about one-sided versus two-sided tests. And we'll talk about, we won't actually work, but we'll talk about using the binomial test for small sample sizes and proportions. So here's our example that we're sort of going to carry through, and this might not be part of the notes, but I think I added it later because I wanted to, as we're talking about the test, actually work through an example in this section. So here, astrologers have prepared some horoscopes for, I believe it's 116 different people. They had volunteered for this. And so they have their birthdays and birth years, and they've made astrological charts for all 116 of these people, and it's supposed to tell you something about the personality. And then all 116 of the people have taken this California Personality Inventory. I think it's what CPI stands for. It's a personality test. And they're going to try to match the results of the personality test with the actual astrological chart to see what's going on there. Specifically, they are given 3 charts at random and 1 CPI. And they're saying which of your charts matches. Now, one of them's right, and the other 2 are people who are chosen completely at random. So it turns out when they do this for all 116 people, they were correct. The astrologers correctly chose the person who actually matched the CPI 40 times out of 116 times. So are astrologers' predictions better than guessing? What would be guessing? If they were completely guessing, what would you expect to happen? They would get it how much of the time? A third of the time, right? And then 40 out of 116, that's what, 0.38 or something like 0.34? Oh, that's barely more than 0.333. So, you know, it is a little more, but we're, of course, concerned with it. It's statistically significant. So that's what we're going to do here, is we're going to go through and see, can we statistically say that they are better than guessing? So our step 1 is our assumptions. Are our assumptions met? These are the 3 assumptions that are specifically for proportions. Our variable needs to be a categorical variable because we're going to have sort of the proportion of people who, so since we're working with proportions, we need categorical categories. Either they are in the proportion or they're not. We do have that here, so either they were correct or they weren't correct. And then the data needs to be randomized, and the data were randomized. We offered the 2 faith choices were randomly selected people. So this data was randomized. Sample sizes are large enough that the sampling distribution is approximately normal. And remember, and this is exactly what we talked about in Chapter 8, in order to do confidence intervals, we needed that sampling distribution to be normal too, and that meant we needed at least 15 successes and at least 15 failures. And that's what this is saying here, at least 15 successes and at least 15 failures. How many successes did we have? 40. And then how many failures did we have? 116 minus something, definitely more than 15. So we're good here too. We've met all 3 of our assumptions. Your project, you probably won't need this 3rd assumption because most people only collected 30 data values. That's all I asked you to select. So you're probably not going to get 15 and 15. We'll go ahead and do it, but know that your hypothesis test for proportions is really kind of compromised. And here, hypotheses. So the null for proportions will always be that the population proportion P is exactly equal to some value. This little piece of 0 is your hypothesized proportion value. And you'll see that on your calculator too. It'll prompt you what's P0. That's your guess.
So P0 would be
0.5. Yeah, you would write it as 0.5, but yeah, absolutely. 0.5, 0.2. It's going to be a number between 0 and 1. And then your alternative here would be always, and this is just to identify, this is actually not part of the hypothesis, but it identifies which hypothesis it is. And then this is the actual hypothesis statement here, and you have 3 choices. greater than, less than, not equal to. And so the greater than, the less than, and the not equal to are all possibilities for your alternatives. You're always going to have your P, you're always going to have one of these three symbols, and you're always going to have some numerical value for proportions between 0 and 1 on that right side. What do we want in this case? And maybe it's better to start with the alternative. What do we want to prove is true for this? It asked us, the question that was asked is, are astrology predictions better than guessing? This is where we're going to make our hypothesis. So we're going to make one of these. Which symbol do we want to choose?
We can choose any one.
Well, we need to choose the one that matches the question being asked. Yeah, P is greater than, and what specific proportion do we want? What does better than guessing mean? Yeah, 1/3. Do y'all see why that's the case in this particular example? Okay, so guessing, if they were to guess, because they're presented with 3 and 1 is right, if they were to guess completely, their proportion would be 1/3. If they're better than guessing, that means they're better than 1/3. So HA in our instance is the population proportion is better than 1/3. Yes, Taylor?
Are we always just supposed to assume that guessing is just going to be a 1/3?
Not always 1/3. It depends on how many they have to choose from. But if they're guessing at random and each one's equally likely, it will be 1 over the number that they're guessing. Any other questions? Okay, and then HO, once you have HA, you can just replace whatever the symbol is with an equal sign. So that would be, yeah, P equals 1/3. And if you don't have the 3 elements, the P or the mu, the equal sign, or in the alternative case, the one of the 3 alternative symbols, and exactly what it equals, I would say that's an incomplete hypothesis. So just saying equals 1/3 is not enough. What equals 1/3? And then also, you don't have to use this notation, but you need to tell me which is which. If it's asking for both, I need to know which is which. So you can literally write out null if you're more comfortable with doing that. Any questions? And then the test statistic is actually where we get a little mathematically hairy, but we've seen stuff that's sort of similar to this before. This is the z-score calculation. Remember that the z-score, way back from chapter 2, and we've done it several times since, is the observed value minus the mean divided by the standard deviation. And on your formula card, it says the standard deviation reminds you that standard deviation could be for the proportionate population, the entire population, which is sigma, or it could be for the sample, which is S, or it could be for the sampling distribution. It is, in this case, for the sampling distribution, which means it's standard error. So here we see our observed value, which is the sample proportion, because our observed value is the sample. We see our mean, or our hypothesized mean, of the entire sampling distribution. And then this is actually the formula for SE, for proportion. Yeah, this first one's P hat, but the rest are P0. Yeah, the hypothesized population proportion. So the thing that appeared in our null hypothesis and our alternative hypothesis. Yeah, it's 1/3 in this case. So what's our P hat? Yeah, we'll go ahead and stick the fraction in, and the 0.34 fraction came from 40 out of 116, because 40 out of 116 times the astrologer prediction was correct. And then we subtract off Somebody's already said it, I think. Yeah, 1/3. And that's our numerator, and if we're putting it in the calculator all at once, which I like to do because it eliminates rounding error, you definitely need parentheses around the numerator. And then the square root, 1/3, that's our P0, 1 minus 1/3, divided by, what's our sample size? 1/16. Hopefully it'll work better than it was. Oh, no, it didn't. Sorry. So that's my numerator, 40 over 116 minus 1/3, and I put parentheses around that. Divided by the square root, and then I don't put any parentheses around this. If you're using the old calculators, it'll put parentheses for you. You can go ahead and leave that alone. But 1/3, open parenthesis, 1 minus 1/3, close parenthesis, divided by 1/16, and enter. And you should get 0.2626. Is that what everybody's getting? Any questions on that? So this is our test statistic. Knowing that this is our test statistic, do you think we're going to reject the null and say the alternative is true? No. Because we are just almost on top of our hypothesized mean right there with 0.2626. We're not out 1 standard deviation or 2 standard deviations or 3 standard deviations. We're out 0.26 standard deviations. So not very far at all. And if we label this on, so this will be, if we're looking at the z distribution, which we are here, this will be 0. That number is 0 right there. This is our z-score, which they rounded to 0.26, but I would prefer that we keep as many digits as possible. And then how would we find the p-value? Normal CDF. And then our minimum, yeah, the 0.2626. Our maximum, our mean, and our standard deviation. And what will that give us? Are there any questions on that? Okay, this is the z-curve, which means it's the standardized distribution, and the z-curve is always the mean of all z's, because z is defined to be how many standard deviations you are from the mean. So it is always centered in 0 with a standard deviation of 1. And that, you might want to look back to the beginning of 6.2, where we talked a lot about that standard normal distribution, to sort of recall that. But at any time we're plugging in z-scores instead of our actual values, we use 0 and 1. We could have plugged in, instead of the z-score, we could have plugged in literally 40 over 116, which was our p-hat. And then we could have plugged in, of course, 199 still there. And then we would have plugged in 1/3, comma, we would have had to compute the standard error for, which is p hat minus 1/3, instead of 40 over, we would have had to keep that denominator and put that there. Any other questions or comments? And then our conclusion, our p-value was approximately 0.40. They rounded more than I like to round, but 0.40. So what do you think we're going to do here? I'm sorry? Well, are we able to reject the null? Yes? No. Okay, good. So what we do when we don't reject the null, we never accept the null because we can't prove something's exactly equal to. So we make a really wishy-washy sort of statement, and we say we cannot conclude based on our data and I always like to phrase it in terms of the alternative hypothesis, because that's what we were trying to prove in the first place. And I like to put it back into context of the problem, back into something that a layman can understand that hasn't had any statistics. So we cannot conclude based on our data that astrologers' predictions are better than guessing. Any questions on that? Does that make sense? So how do we interpret the p-value? We sort of just interpreted it, but we had a really easy p-value. When it's 0.4, it's pretty obvious 40% of the time you could get this data that's a really high percentage, so it's not extreme, it's not unexpected, it's nothing that you would say, oh yeah, that proves the null is not true. The burden of proof we actually place on the alternative hypothesis, which means that we need a very high probability that the alternative hypothesis is true before we'll say, yeah, let's reject the null. So it's the same sort of thing in a court trial, right? The burden of proof, you need a very high probability that the actual person is guilty before you're actually going to say that the person is guilty and sentence them. So the same sort of thing here, you need a high burden of proof. If the p-value is small enough, the data, we will say, do contradict our null hypothesis. And in that case, we'll say the alternative is true. So if we reject the null, we accept that the alternative is true. So we really are left with two sorts of decisions here. Do we reject or do we not reject? And I think of Hamlet to be or not to be, to reject or not to reject here. We have the symbol that I told you about, the significance level alpha. And we will set alpha. I may have added some stuff here, or switched it around a little bit.
I'm like 5 slides. Totally skipped over.
Okay, I switched some stuff. I'll probably do those slides, but just in a slightly different order. So the alpha is what we're going to set before we run the hypothesis test, before we even look at our data. We'll say we want to do it at such significance level. And the most common one is 5%, so 0.05. So if our p-value is less than or equal to 0.05, most of the time, as long as we've agreed that that's our alpha, we reject. And if it's more than 0.05, we say we don't reject, like we did previously when it was 0.4. We said we don't reject. We cannot conclude really anything. So less than or equal to, reject. If our p-value is more than, don't reject. So a lot of people, I think this is where they have trouble. because the calculator will do a lot of the stuff for us, but they don't know what to do with the p-value. They don't really understand what that p-value means. Heather?
It's being, for like 0.5, had it been 0.3, we would have rejected it.
Yes. Our p-value was 0.40. So if our p-value had been 0.03 instead of 0.40, then yeah, we would have said was rejected and say astrologers' predictions are better than yes. That's because it's below the traditionally accepted significance level. And what that means is, if you had had a p-value of 0.03, that would mean literally 3% of the time we would expect to get data that's this extreme if it were exactly equal to 1/3. And so, since 3% is such a small percentage, it's not very likely that our null is actually equal to 1/3, because that is our actual population proportion. And because of that, we conclude that it really is better than guessing. And now, of course, our conclusions are not 100%. So we would say, based on the alpha value of 5% or at the 5% significance level, we can conclude it. But that gives you a little, there's error. There's going to be error. Any other questions? If it doesn't state it, you always use 0.05 or 5%. If it does state it, though, you change alpha. So here is our, again, alpha value. Like I said, the most common alpha value is 0.05, and we reject the null whenever p is less than or equal to our alpha value. And when we reject, we say that we do have statistically significant results. So we would say we can conclude that astrologers' predictions are statistically significantly better than guessing. We may throw out the statistically because that makes it hard to sort of flow. But when we say significantly, we mean statistically significant. So here is sort of a spectrum on possible values of p. Really, unless you're a very bad guesser, you're not going to have things that are more than half very often. Because what that means is that you guessed that it was less than 3, it was actually more than 3. So most of the time, we're going to be in this region anyway. And what we're saying is that we will only reject when we're in this very small region, generally 0.05 being that very small region. So when the p-value gets into that very small region, that's when we say, yep, that's when we're rejecting. So that's small enough. How small is small enough? That's generally what's accepted as small enough. And if we decide to use something other than 0.05, we need to make that decision before we actually do the data. For your projects, I'm pretty sure they're just 0.05. In a lot of instances, you're asked to interpret the p-value. What does this p-value really mean? Well, we've talked about the fact that the larger p-value, the weaker your evidence is against the null, essentially. So p-values of 0.4 and 0.3 and that sort of thing are just so huge that you have almost no evidence against the null. But when you get down to between 0.1 and 0.2, so 10 to 20% of the time, some people actually consider that quasi-acceptable in certain circumstances. So I said that that was sort of weak to moderate when you're between 0.1 and 0.2. Not very often will you see people who want to accept something in that range, but sometimes you will run into people who want to accept 0.1 to 0.2. Then this one you'll see pretty frequently. So it's not the most common one, but if you're between 0.05 and 0.1, which means 5 to 10%. So if you're in that range, a good deal of people say, yeah, that's okay for me. I don't need less than 5%, 5 to 10% is okay for me. So that's what we consider moderate. Most of the time, though, people want either strong or very strong evidence against the null. So strong evidence against the null would be 1% to 5%, or 0.01 to 0.05. That's considered strong, and then very strong is anything that's less than 0.01. So this isn't something that the book tells us. I thought that it would be nice to have sort of a guideline. So when you're asked how strong is the evidence against the null, you sort of have a rough idea here. And this isn't something you necessarily need to memorize, but just sort of understand where they're getting this from and how this is being decided, to give you a rough idea of what's strong and what's not. And then the stronger the higher your p-value is, the less your significance is, the less significant. And the converse is true too. So the lower your p-value is, the teeny tiny p-value, the very strong, very significant your results are. It tells how strong the evidence is against the null. How significant. Okay, significant. Yeah. So because this is true, we don't want to just say, yeah, we conclude this or we cannot conclude this. What we want to do is also tell our audience the p-value. So it's very important to tell our audience the p-value when we're recording this. And as an audience, it's very important for us to consider the p-value when we're looking at data. So, for example, some people may say, because the p-value is equal to 0.15, we've decided to reject the null and accept the alternative. But you might look at it and say, there's no way that 15% of the time I find that acceptable to reject. So be sure that you think about the p-value, because a 0.15 is very, very, very different from a 0.0000015. So if you have those sorts of results, you're like, whoa, I have a whole lot of faith that this is right. When you have something like, even like this, 0.049, most people would say, yeah, our results are significant there, but you can't put an enormous amount of faith in it. Don't bet the bank on it, in other words. Because what that means is that, almost 5% of the time you're going to have data that's that extreme. And 5% is not that P90. I mean, it's certainly within the realm of possibility. 1 out of 20 times you're going to have data that's that extreme. So keep that sort of thing in mind. The p-value is probably even more important than your actual conclusion. But understanding what the p-value means is. Okay, so do not reject. It's not the same as accept when we're talking about the null hypothesis. So remember that we never, ever accept the null hypothesis to be true. And an analogy that it has here is considering a legal trial. So in a legal trial, your job is not to decide if you're part of the jury. Your job is not to decide if the person is innocent or not. Your job is to decide if there is evidence beyond reasonable doubt that the person is guilty. So you may believe the person is guilty with an 80% chance, but you may say, that's not beyond reasonable doubt because I have 20% doubt that the person is guilty. So in that case, you really are directed to acquit. And acquitting doesn't mean you're saying that that person is innocent, because you may believe that more likely he's guilty than innocent. But it's the same thing here. We may believe that it's more likely, especially if we had had a p-value of 0.10 on our astrology predictions, we might have thought, well, it's more likely than not that they're better than guessing, but we don't know beyond reasonable doubt. So, keep that in mind, that anytime we say don't reject, that doesn't mean we're saying that it's true. So we're not saying that astrologers' predictions are exactly equal to guessing. Are we getting phone calls? That's wrong. Okay. So, very different things. We never really say the null is true. We do have two-sided significance tests. Everything we've drawn so far has been just shading one tail. But if we have the not equal to symbol, we have to shade both tails. Because remember, we shade in the direction of the symbol. Well, if it's not equal to, that means that it can be greater than, or it can be less than. So what we do in that case, we'll take our Z4, and then we'll take the negative of our Z4, and we'll shade the area to the right of the Z and to the left of the negative Z. And both of those areas add together to be our p-value. In other words, this doubles our p-value. So we can find this area and multiply it by 2, because it's perfectly symmetrical. So whenever you have not equal to, it's doubling your p-value. So it's even harder to prove not equal to because you have bigger p-values than it is to prove that it's strictly greater than or less than. And then here are, and your notes are probably wrong, but here are the 3 tails. So for, I think you have 2 that are 2 tails, and it's supposed to look like this. Okay, so I guess it depends on where you printed from. Somebody yesterday said.
No, ours don't. You're right.
Okay.
Yeah.
Okay. So when you have greater than, you're going to shade the area to the right. When you have less than, you're going to shade the area less than or to the left. And then when you have not equal to, you're shading both areas. Any questions on that? Okay. So if I know these say 0 here, but it's representative of the original distribution, and the original distribution would have mu equals 1 here. So if you're saying your mean is 1, that's your guess. You are not going to reject that null hypothesis if you've got a hat or something very close to 1. But you will reject it if it's way less or if it's way more. So what these are sort of the regions that you would reject. So you would reject it over here, and you would reject it over here. So you've got to consider both sides.
But you're saying anything past 3 standard deviations of this.
Yeah. So even if you were doing a 2 tails, because 2 tails would be 0.003 or less if it's past 3 standard deviations. Astrologers' predictions are not the same as guessing, maybe? That sort of thing? Is that a good, does that tell you? Yeah. Well, it's just one example. I mean, it could be worded lots and lots of different ways. Yeah. Does that answer your questions, Randy?
Are we going to do examples?
Yeah, we'll do lots of examples. Okay. So, we have one-sided and two-sided tests. If you are the one deciding your hypothesis, which you are, of course you already have sort of, for your project and for your activity, this is the way you will decide, or should have decided. Of course, hindsight. But in the future, if you ever come across doing a study, you should first consider the context of the real problem. So, when you want to prove that astrologers' predictions really are better than guessing, so if that's what you want to prove, then you definitely need to use like a right-tail test or a one-sided test. If you want to prove that something's better than something else or worse than something else, that sort of thing, you need one-sided. So consider what you really want to prove in the context of the problem. And then, if you don't have anything that's just a burning sort of, it would be really better to use this, then go ahead and go with equal, or not equal, the two-sided test. Because most research uses two-sided tests, and you've got confidence interval and hypothesis testing agreeing if you're using the two-sided test. So if there's not a compelling reason to use greater than or less than, go ahead and use not equal to. Any comments on that? Okay, and it turns out that if you are doing significance tests for proportions, you need at least 15 successes and at least 15 failures to do the method that we're just talking about, the 5-step process that we've just gone through. If you don't have 15 successes and 15 failures, you really should never do this test. But you can do a different test. It's called the binomial test for small samples. And actually, Minitab will do this test too. There's a little box that you check to tell it to use for large samples. And I think I want you to actually check that box, because then if you check that box, your numbers will match what you've done in the calculator. If you don't check that box, your numbers won't match, but they'll actually be more accurate, because this binomial test is what we're supposed to use whenever we don't have at least 15 and 15. So remember, we had that voodoo magic for confidence intervals. This is sort of like that. It's not quite voodoo. It's actually a bit sounder than that, but it uses the idea of binomial distributions that we sort of skipped over. But that's okay. We're not actually going to do this test unless you accidentally do it on Minitab. But you're supposed to check that box about large samples, even though we don't have it, so that you can compare your results. But there will be questions in your homework, and I think your paper homework, about what could we do if it didn't meet the assumptions. And the answer is you could do the binomial, or somebody else could do the binomial. You plan to apply significance testing to your own experiments of testing astrology. And in your experiment, you decide to give them 4 personality tests, 4 personality things, one of which is right, and of course 3 are randomly chosen that are incorrect. Define the notation and state your hypotheses, and here you're going to assume the possibility that predictions could be better than random guessing, pretty much like we assumed before. So what would your hypotheses be? Yeah, C is greater than 1/4, and the other one would be sorry.
It says equal to 50.
Equal to
I'm like, which one?
equal to 1/4. And which is which? Yes, Heather.
Okay, no matter, I get it now. The bottom one is HA and the top one is
Yep. Yeah. And the reason it's both P is because we're dealing with proportions here. Our data is not averages or means. Any questions? Here we have given to us that the null hypothesis is P equal 0.50. And our test statistics equal 1.04. Okay, so that's our null hypothesis and our test statistics. We want to find the p-value for what if our alternative is this? So we're gonna try to find the p-value. How could we do that?
By going to the
You do P hat minus P.
parentheses,
Or
square root of.
Do we have t-hat?
No. We've got the test, we got the z test.
We've got the z.
So that is the,
Oh, that's fine.
We'll do the p hat minus
The z
po
square, yeah.
divided by the square root of po.
Yeah, that's how you got the z score, they got
You
it.
do this almost,
Yeah, but before that, we wanna draw. Yeah.
I'm like thinking of some mathematical,
Okay, so, because this is the z score, the center is 0, and our test statistic is 1.04. If our alternative hypothesis is p greater than 0.50, where are we gonna shade?
Right.
To right. And then, we're gonna, as Taylor said, we're gonna do normal CDS.
1.04, yeah, 1.04, 1 0.
Are there any questions on that? Okay, and what will that give you?
0.1491.
Okay. And then, we're asked not equal to. What will we shade in that case?
Everything else.
Okay, everything else?
Oh, the complete opposite, so you would do negative.
Yeah,
one.
negative 1.04, and then shade right tail. But then we want both this green tail and the blue tail, right? And even though I haven't drawn it perfectly, they should be perfectly symmetrical, which means that you just double,
Double the.
yeah, so we'll take this one and we'll multiply by 2, and we'll get
0.2983.
any questions on that? Okay. Right. So C is less than 1/2. What do we shade then? Everything to the left of, yeah, positive 1.04. So, because this is still our test statistic, we shade everything to the left of the test statistic. And then if we were to do normal CDS here, yeah, our lower limit is negative 1.899, and then, yeah, 1.04, yeah, 0.1. And what will that give us? Thank you. And if I were to add the red to the blue, what would I get? 1. So we could have just subtracted the blue from 1 if we've already known the blue. That's another way. Any questions so far? Do any of these values give strong evidence against the null? And if so, which ones? And why? They're all weak. Or moderate to weak. This one might be considered moderate to weak for some, good enough for some people. But none of them are going to be strong. And again, remember our chart that we had, the smaller P is, the stronger the evidence. So if you're less than 0.05, you've got strong evidence. If you're less than 0.01, you've got very strong evidence. But when you're more than 0.1, you've got weak to moderate. When you're more than 0.2, you've got weak. So remember that sort of thing. Does that answer your question, bring you to be a sort of question and answer.
But if it was,
Any other questions?
so, changing the values, if that overall .1491 would have been .014, it would have been stronger.
Yeah, that would have been quite strong, yeah.
So if there's any difference to the national system, we believe that this is going to happen with those numbers, then our conclusion would be,
I would say we cannot conclude that whatever the alternative, that the, population proportion is more than 1/2 with the data that we have. A lot of people say there's insufficient data to conclude. So that implies that if there were more data, you might be able to conclude. We're just not sure, but the data that we have, we can't conclude.
so we're going to throw out the null hypothesis, or not throw out the null hypothesis, and the conclusion is either going to be, we conclude that this is not true, or we can't conclude this.
Yeah. We conclude that this is true, or this is true, or this is true. So you really conclude the alternative, to phrase it in terms of the alternative. So if it had been, as Michelle is saying, if the first one had been .0149, we would say we can conclude that the population proportion is greater than 1/2. So we try to phrase it in terms of the alternative hypothesis. Because you're rejecting the null, whenever you reject the null, you accept that the alternative is true.
So what we want to say is, if you're going to throw out, if you're going to reject the null hypothesis, then you are accepting the
Yes.
alternative hypothesis.
Yes.
Okay.
Any other questions or comments? We want to sign the test statistic and p-value. So here is our null hypothesis that p is equal to 1/2. So I believe that's the same that we had on the previous. Here is our sample proportion, and this is based on the size of 100. We want to show that our test statistic z is exactly equal to -3.
Okay, this is where we would actually go and do the square root divided by all that, that big formula.
Mm-hmm. So the formula is p hat minus p0.
Divided by the square root, 0, multiplied by 1 minus 0, divided by the number.
So our p hat is, our p0 is, and again, putting this in the calculator, be sure to put parentheses. P0, again, or minus 0.50, all over 100. And what's that going to give you? -3, yay! Any questions on that?
Those are separate things. They're not the same problem, or,
This is part A. Does that answer your question?
no, okay, you got the 0.35 on the top, that's not the numerator, and then the denominator is the numerator, 5 up there.
Okay.
Two separate. Okay, you got 0.35 there.
Yeah, this is the numerator, and this is the denominator. But if you look under the square root, you would say, under the square root, this is the numerator, and then this would be the denominator. But if you do, on the calculator, open parenthesis here, close here, divided by, and you have the new calculator, so it doesn't do a parenthesis under the square root, but certainly this whole thing needs to be under the square root. And you would just literally type this in, open parenthesis here, close here. So the only places you need parentheses are right here. So these two sets are the only parentheses that you need. Does that answer? Okay. Any other questions?
So that was correct, like that.
Yes. Really, it told us the answer, and we were confirming. Okay. Now we want to find what the p-value is. So, I like to draw a picture for these. Here is 0 in the center. Our z-score is -3. And then how are we going to find the p-value is less than? Right. Which part are we going to shade though? Yeah. What if it had said greater than -3?
Everything is right.
Or yeah, greater than 1/2. Yeah, we would have shaded this whole big region. So you don't always have to shade the tail. We normally are shading the tail, but that doesn't have to be the case. You shade in the direction of your alternative symbol, not in the direction of the tail. So, normal CDF. Yeah, -1.99. -3. And what will you get? Uh-oh. 1.33? 3.4?
Yeah.
Error messages could be if you use inverse norms. If you use a minus here instead of the negative, or a minus here instead of the negative. Also, perhaps if you use alpha E instead of the second comma. Did you figure it out? Okay. Any other questions on this so far? Okay. Does the p-value give much evidence against the null? It is strong. It's actually very strong, isn't it? So very strong because it's so small. Any questions? Much, much less.
Oh, much, okay, I thought I was reading.
Not just a little less.
A lot less.
Yeah. Less. Who wants to do this on the calculator?
OMG. I thought that was easy. You're mean.
That test one prop. Well, actually, I think I did this way in the last class and in yesterday's class. And I thought that people understood better on where all this stuff was coming from.
Oh, okay. I was like,
So-
awesome.
No, I'm not doing it for you. I promise. So that test, and then which option do we want to use? Nicole already said it, so she knows, but does anybody else? Yeah, 5. Because we want to use the test, because remember when we talked about confidence intervals, the first ones were for hypothesis tests, and one prop Z is the one we want to use. So our P0 is our hypothesized proportion, and what is that in this point? 0.5. But the rest of it, I think, is not in this problem. The X, the number of successes, we're not explicitly told that in this problem. But what are we told? We're told the sample proportion, and we're told the sample size. So do you think we could find X? How would we find X? Yeah, multiply the sample size by the sample proportion. So 0.35 times 100. If this weren't a whole number, you should make it a whole number, because X always needs to be a whole number. So if it were 35.2, round to the nearest whole number. And then our N is 100. And our symbol, well, we wouldn't even know a symbol for A, but it turns out A is just asking for the Z-score. The Z-score is the same no matter what symbol we press. But B tells us which symbol to use. It tells us to use the less than, right? That's less than. So we use the less than symbol, we highlight it, press enter. And so when it calculates the p-value, it will say, oh, remember alternative is less than, so shade less than. And then calculate.
I'm depressed now, I'm like.
Excited, you're excited now.
Oh my
Because it's so much easier than you thought it would be, right? Z equals -3, so it tells us our answer to A, Z equals -3. It tells us our answer to B, our p-value is 0.0013499672. And then it tells us p hat and n, so we confirm that, yeah, we did it right, we got the p hat of 0.35. It tells us our alternative hypothesis right up here. It doesn't give us our null, but it does give us our alternative. Any questions?
I got P hat, but I got different things with P.
Okay, it's probably because you don't have less than right here.
Oh, well, yeah.
So, go back in and change it to less than and hit enter. Any other questions? Okay. So I really want you to use the calculator most of the time, but I wanted you to go through some non-calculator examples so that you would know where this stuff is coming from and why, if it's a negative extreme z or a positive extreme z or a small p-value, that sort of thing. So know where those things come from and what they mean. Okay, garlic to repel ticks. We have a recent study where they did daily consumption of 1,200 milligrams of garlic, and they said that this would reduce tick bites. The ticks were afraid of the garlic. And so they did a crossover design. What does that mean?
That means that they think sample somebody else will switch.
Yes, so the same person actually receives both treatments. That's exactly right, but the way I would phrase it, the same person received both treatments. So they would randomize probably the order of the treatments, whether they received garlic first or the placebo, but every person in the study received both, and they went through a period of receiving both. Of course, I can't imagine a placebo would actually smell like garlic, so they probably weren't exactly a blinded study. But they did this, and then 37 of the subjects said that the placebo, or that the garlic was more effective. 37 said garlic was more effective at repelling ticks, and 29 said that the placebo was more effective at repelling ticks. Does this They were probably out in the woods. Anyway, they were Swedish conscripts who probably were out doing stuff in the woods.
See people laying in bed of ticks and like.
No, I don't think they did that. I think they hopefully had to be in the woods anyway.
Oh,
So they weren't like, and they're not that droll to. But they're trying to help them in the end. We'll take in garlic's help. So does this suggest a real difference? Obviously, there's a difference, but this is a significant difference. And we'll determine that statistically by analyzing the numbers. So what is the variable that's being measured here in this study? Whether they're taking garlic or the placebo, right? And really, measuring whether they prefer, whether they feel that garlic is better or the placebo is better. So, we'll call it medication. I'm not sure why it's medication, but we'll call it nicotine medication here. Which medication was better at repelling ticks? So that's the thing that you'll actually measure and record, the end result that you care about. And then what's the parameter? I'm sorry? Well, it wouldn't just be, it's not exactly that, because all they're recording from these 60-something people is which they said was better. So the data that they have is going to be garlic, placebo, depending on which they thought was better at repelling tick bites. So they're not actually going to record the tick bites, the number of tick bites or anything like that. They're just going to ask which was better. But how would they measure that? So parameters, what parameters have we talked about so far? The mean, and proportion. And would you be computing a mean here, or would you be computing a proportion? Proportion. So the parameters here, and if we put it in context of the problem, it's going to be P, but that's the population proportion, who felt garlic was better. And I guess we could have said placebo, but you usually phrase things in terms of the thing that you're trying to measure in the first place. So the proportion of people who said garlic was better, that's going to be our population parameter, P. I'm sorry? Who felt garlic? Oh, which medication was better at repelling ticks? The P, I have comma, population proportion.
It looks like a greater than.
Oh.
That's why I was like,
Sorry,
that's okay.
P, comma. I tell you what, I may have already told this, I repeat myself often, and just, sort of, like that. But, I went to the parent teacher conference, and I sat down with the teacher, and they were like, and she's a little bit different from me, but I did see some similarities here. But Emma, man, I sat down at her teacher, and she's like, she's doing really well in reading, she's doing really well in math, but the thing is, she can't write. She's doing cursive, and we hadn't taught cursive. It's not supposed to use cursive. And I tell her not to use cursive, and she writes in cursive. I don't know what she did that.
That's why I was like, really?
Yeah, sorry.
It's the whole grade.
I do try sometimes, and I know that's sad, but I'm trying.
Yeah,
Still,
I can totally do
yeah,
that.
sorry. Please ask anytime anything's so big. Well, most of the notes are typed. Stating hypotheses, or what would our alternative hypothesis be? What are we trying to prove? Does this suggest a real difference between garlic and placebo? How would we show that with the population support? Or 0.6, right? Yeah. So P greater than 1/2 would mean there's a real difference. Does that make sense? Actually, it says a two-sided test. I would be tempted to do greater. It says a two-sided, so we should use, instead of greater, not equal. Yeah. So that's our alternative hypothesis. And then our null hypothesis would be equal. Yeah, P equals 1/2. Any questions on this? And basically, if you have something that's not a half, statistically, is not equal to a half, clearly not equal to a half, then what that means is that one is better than the other.
In other words, we need to take that because it's very much worse than the placebo.
Well, you would formulate these before you saw the data. So you might say that garlic attracts ticks. So we want to find out. We're not really sure what garlic will do. We want to find out if it makes it better or it makes it worse. Right, before you're formulating your hypothesis. Any other questions? Okay, so let's do this on the calculator for C and D. It says find the test statistic value. So what are we going to want to do on the calculator? And our P0 will be 0.5. And our X, number of successes, 37. And then our N, 37 plus 29 or 66. And I can just literally, since I'm not very good at arithmetic, put in 37 plus 29 and it'll give me that answer. And then which symbol? Not equal, so I highlight not equal and press enter. And once I have all of that, calculate, enter, it tells me proc not equal to 0.5. Tells me my z-score, which is my answer to part C, or D, whichever part this is. Finding the test statistic is 0.98. That's not very big, right? Not even 1 yet. And my p-value is 0.3247, which means 32.5% of the time we would expect to get data as extreme as the data we have if it were, in fact, exactly equal. So, what do we conclude here?
Include the pluses.
You're proving your alternative.
You want to prove your alternative, did we? No. Yeah, we have bad or not enough data, really, because our p-value is actually the point, what was it, 324, 25, if we round. And since this is so large, then we can't prove anything. So we say we cannot conclude essentially that there is a real difference, like the problem phrases, that there is a real difference between garlic and a placebo, other than this variation. Yeah. Heather? That's the z-score, or in the next section it'll be the t-score. Just like z, but it's because you have, degrees of freedom, and it's an extra sort of buffer because of the S instead of the C. No, if you get, it gives you the degrees of freedom, you literally read straight across. So, yeah. Any other questions? Here we've got something relevant to what you're probably into right now with doing the Minitab stuff. So we have 49 students in a class at the University of Florida who did blinded studies for Cola-Cream. 49 compared Coke and Pepsi, and Coke was preferred 29 of those times. In the population that this sample represents is this strong evidence that a majority prefers one of the drinks. And this is actually the Minitab data with those results. So we want to first explain how would we get the test statistic off of this Minitab? Yeah, let's read the p-value off. And these two questions, the first two at least, are very easy. And then how would we get the p-value? Are you the one that says p-value? So, and then how would we interpret this particular p-value? What would you say about that p-value? That is weak. So not very likely to prove that, a majority prefer one of the beverages over another. Based on the results, does it make sense to accept the null hypothesis? So, we're not choosing the alternative. Yeah, we never accept the null. Because the null would be saying that they're exactly equal. And even our data that we have doesn't say that. Our data that we have says that 59% prefer Coke. What does a 95% confidence interval tell you that the test doesn't? Yeah, so it tells you exactly the range that will most likely hold your P, whatever the population proportion, true population proportion is. And our hypothesis test, in this case, we would conclude basically that we don't know anything, that we cannot conclude that the proportion is more than 1/2 or less than 1/2 or not equal to 1/2. So really, in this instance, it just tells us that we don't know anything, our conclusions for the hypothesis test. So this tells us a lot more in this instance. Another student in the other class asked, well, why would we even bother if the confidence interval is going to tell us more? And really, it's because most of the time, we don't want to know the exact range it is. We want to try to support some preconceived hypothesis, like our product is better than this other product, or there is some bias here because not all things are equal between these two groups, or something similar to that. So most of the time, we're not going to want to know the exact range. We're going to have some sort of ideas and theories that we'll want to prove or support with the data. So that is all of the proportions. Next time we will go through and talk about the means, and we'll work through an example with how to do the means, and we'll talk about the 3 different tails when you do means instead of proportions, and see how they're all mu's instead of p's. We will also talk about how a specific case of two-sided tests and confidence interval results, they actually exactly agree when you're doing it for means. We'll talk about the robustness, what happens if it's not normal, and we'll talk about looking at our data even though the test is robust. So those are the sorts of things that we're going to do next Tuesday. The quiz and the test and the homework and everything for Chapter 9 is due on Tuesday, even though I moved the project back to Thursday. So do as much of Chapter 9 homework as you can, certainly through 9-1 and 9-2 of the paper homework and the online homework, so that you'll be ready to just wrap it up next Tuesday.